All right, let's talk a little bit about acids and bases, which is a pretty important topic in chemistry. So what I'm going to do here is give you some basic definitions for acids and bases, and then I'll give you some specific examples of how they differ and how you can use these different relationships for each other. Okay, and so basically there are three different definitions for acids and bases. And what I want to get across is that it isn't really the case that one of these definitions is better or worse than any of the other ones. They're just different ways of looking at it. Okay, so the first one was put forth by good old Svante Arrhenius, a Swedish chemist, in the late 1800s. And Arrhenius defined an acid as anything that can donate H+ ions to a solution. And he defined a base as anything that can donate hydroxide ions or OH- ions to the solution. So most of the things that you think of as typical acids or bases fall into the Arrhenius category. Okay, for example, HCl can break apart into H+ and Cl-, so there's my source of H+ ions. Or something like sodium hydroxide, NaOH, can break apart into sodium ions and hydroxide ions, so there's my source of OH-. Okay. Another definition is that of the Brønsted-Lowry acid or base, and this was about 40, 50 years later, 1923. And Brønsted-Lowry liked the Arrhenius acid thing. They kept that. Okay, so we still have an acid as a proton donor, but we're going to change the definition of a base. Instead of it being a hydroxide ion donor, this is going to be a proton acceptor, which kind of makes sense, right? If you have some kind of transaction where I want to donate something to you, it's not really a full-fledged transaction unless you also accept or take the money, right? So for every donor, there has to be an acceptor. Okay, so Brønsted-Lowry defined a base as a proton acceptor. This is a little bit more general. You don't necessarily have to have OH- ions around. Anything that can pick up a proton could be an H+ acceptor. And then the last definition for acids and bases that I want to show you is that of Lewis. Okay, this is the same Lewis as Lewis dot structures. Okay, so clearly the guy liked electrons. Okay, and so we're going to define a Lewis acid as something that can accept electrons, and a Lewis base as something that can donate electrons. Okay, so what I'm going to do now is give you some specific examples of how these different acids and bases can sort of relate and differ from each other. Okay, so in the Arrhenius theory for acids, this was the simplest definition that still works, but it doesn't really give us like numbers for things. Okay, you can use it to describe relationships between things that are very strong and donate a lot of H+ ions or a lot of OH- ions, and it's based on dissociation, but it doesn't really give you like a feel for chemical reactions and what happens in between. Okay, and so Brønsted-Lowry is kind of the next step. After that, let's look at these things as far as actual chemical reactions that have reversibility and equilibrium, as opposed to these Arrhenius equations where it's just going in one direction. Okay, and so we're going to start with the Brønsted-Lowry acid, okay, HA, or HA for short. Okay, and so this is going to be my acid, and the H is there because it's a proton donor. The A could be anything. Okay, I don't know what the A represents, but the rest of the molecule. And what's going to happen is this thing is going to be dissolved in water. So as soon as this hits H2O, okay, it's going to break apart or dissociate into H+ ions and A- ions. The A- ions are right here. The H+ ions latch onto the water to make H3O+, which is called hydronium ion. Okay. A base, remember, is a proton acceptor. So now when this reacts with water, the water breaks apart or dissociates into H+ and OH-, and now this H+ gets accepted by the base, so it becomes BH+, and the OH- that I generated is still hanging out over there. So you can see how this is kind of similar to Arrhenius, right? In a Brønsted-Lowry acid, I eventually generate hydronium ions, and in a Brønsted-Lowry base, I eventually generate hydroxide ions. Now, the nice thing about Brønsted-Lowry acids and bases compared to Arrhenius acids and bases is there's this notion of equilibrium, where things can go back and forth. Okay. When I go back and forth, the things on the left side produce the things on the right side. And things on the right side are sometimes called conjugates. And so if I have an acid, I can create a conjugate base. If I have a base, I can create a conjugate acid. The conjugate base would be in the reverse direction, right? In other words, if I look at this A minus, and I were to react it with water, or react it with H3O plus, in this case, it would gain a proton and make HA plus OH minus, or in this case, make HA plus H2O. And so the point is that the A minus and the HA are conjugate pairs. They always differ from each other by a single H plus ion. I can do the same thing for the conjugate acid of the base, BH plus, right? This could react with water to give me the base again, plus a hydronium ion, or it can react with maybe a hydroxide ion to give me a base plus H2O. Once again, the conjugate acid and the base differ solely by a single H plus ion. Now, in Brønsted-Lowry, you can have things that are called amphoteric. Okay? In Arrhenius, it's pretty clear that something is an acid or something is a base, depending on whether there's an excess of H plus ions or an excess of OH minus ions. But Brønsted-Lowry is a little bit more general. There are some things that can act as both acids or bases, right? Everything is relative. So it kind of depends on the relative strengths of the abilities to donate H plus ions or the ability to accept H plus ions. So if something can act as either an acid or a base, you call it amphoteric or amphiprotic. Water is a famous example of that. Okay, and you saw that a second ago. If I take water and react it with a strong acid, like HCl, that means that the water has to act as a base because the HCl is a strong acid. If it acts as a base, it accepts the proton, okay, so to form hydronium ions and chloride ions. So we can say that the hydronium ion is the conjugate acid of water. But in this bottom example, the water is actually acting as an acid, and the ammonia is acting as a base. So the ammonia accepts the proton, and the water loses it. So since the water lost it, it's an acid. The thing that it formed is the conjugate base, right? So we can say that hydroxide ion is the conjugate base of water. So if it can act as either an acid or a base, how do I know what's going to happen? Well, the short answer is it depends. Sometimes it can be an acid, sometimes it can be a base. You have to kind of compare who else is in that equation, okay, and look at relative strengths of the acids or the bases to each other, okay. The bottom line is reactions will always go, at least spontaneously, in the direction of the weaker acid or the base, okay, and so you always tend to go from strong acids or bases to weaker acids or bases. Now let me give you a little bit of a flavor for Lewis acids and bases. Okay, remember we said the Lewis base is an electron donor, and a Lewis acid is an electron acceptor. Okay, so here's what's happening. Over here I have two electrons in an orbital. They can be donated to this empty orbital. So this is going to be the acceptor, the thing that receives the electrons. This is going to be the donor, the thing that loses the electrons. And then right here is the bond that maybe forms, like a coordinate covalent bond, between the Lewis acid and the Lewis base. Okay, and so typically in a Lewis acid Lewis base reaction, you transfer electrons from a filled orbital to an unfilled or empty orbital.